Before discussing Einsteinian relativity, I want to talk about Galilean relativity. One of the key ideas in relativity is that of inertial frames of reference. A frame of reference is just a coordinate system, such as you see here. The inertial term means that it's moving with uniform velocity. Now, normally we don't think about coordinate systems as either moving or not moving, but when we're dealing with relativity, that's kind of the whole point. We're interested in the relationship between moving observers. So in the diagram, you see a couple of coordinate systems in what's called standard configuration. Now, this is something we use for simplicity. It actually captures completely all the physics, but it just simplifies it by reducing the motion to along the x and x dash axes. We have two coordinate systems here. One we'll call S and the other S dash. Its coordinates will be denoted by dashes. And the relative velocity of these two coordinate systems is along their respective x and x dash axes in the positive direction. And we usually think about it as the S dash system moving in the positive x direction. Usually think of the S system as stationary in the frame of the page and the S dash system as moving in the x dash direction. Now, time is also going to turn out to be very important, but as far as Galilean relativity is concerned, the time in the S system is the same as the time in the S dash system. This is just Newton's idea of absolute time, which is actually wrong, but for the purposes of Galilean relativity, the relativity of hundreds of years ago, they're the same. The other thing about standard configuration is that the two coordinate systems are oriented in the same way, so that at time 0, t equals t dash equals 0, the coordinate systems are on top of each other. That is, the origins are the same. Just to be explicit about that x equals x dash equals 0, and we're dealing with 3 dimensions. So all this at time 0. So again, these are just conventions that define the standard configuration and make our calculations as simple as they can be. We could, of course, have coordinate systems that are oriented any which way relative to each other. For example, if S was like that, we could have S dash rotated relative to it. We could also have it moving in any direction, not just restricted to along the x and x dash directions. That would not be standard configuration. We could do all our calculations. It would just be a lot messier, and it doesn't add anything to the physics. It just complicates the mathematics. So we stick with standard configuration. The x coordinate of the S dash origin is vt, where v is the velocity of the S dash system along the x-axis. This means that the coordinate of a point in the x dash system is its x coordinate minus the distance between the two coordinate system origins, which is just vt. So that's how you transform the x coordinate. Now, of course, the y coordinates and the z coordinates are exactly the same because there's no motion along those directions. So if I add time to that, these are known as the Galilean transformations. They tell us how to go from S coordinates to the S dash coordinates. We could also invert them and solve for x in terms of x dash. And all that happens is that the sign of the velocity changes. The others are all the same. S dash is fulfilling the role that S used to do, and the S coordinate system is moving in the negative x dash and x direction. So the sign of the velocity is changed when we jump to the S dash system, because S is moving in the opposite direction relative to S dash. That's known as the inverse Galilean transformation. Now, if we take the Galilean transformation and divide it through by time, we get, and if the coordinate is the coordinate of something that is moving in the system, so maybe a little ball that's moving with some velocity u sub x, then what we've got is that its velocity in the x dash system is its velocity in the x system minus the relative velocity of the two coordinate systems. So this is just distance over time in the S dash system, distance over time in the S system. So the velocities in each of those systems, and they're related together just by subtracting off the relative velocity of the two systems. Straightforwardly, the velocities in the orthogonal directions are unchanged between the two systems. These are known as the Galilean velocity transformations, and they're pretty obvious, pretty intuitive. They're the sort of thing you use in your everyday life when you're driving a car or walking around to judge relative velocities.